Yeah? Okay. Now we're going to click this link because it's actually an SVG that would not render properly. Oh, and of course Google Chrome isn't going to render it properly. Only Safari will. It's worth it, I promise. No red bookmarks. Okay, so now we can kind of see this. Oh my god. I hit the wrong button, guys. I'm sorry. Forgive me. Okay, now we can see that there's a red line here. Okay, here's where it's going to get real. We're about to learn about how every audio device that you listen to makes its waveforms. Okay, this is probably the coolest and weirdest part of the whole presentation. And we're going to start with applying noise. So random wave. We're just going to generate a random wave. It's going to be noise. It's going to sound terrible. We're going to take it. We're going to apply it on top of the desired waveform. We know what we want it to look like because we have it in a digital form. So this is all being done digital. Let's step out of audio or analog. We're going to be doing this all in a processor. This is all code. Okay? So we're going to take our digital waveform, represented by some sampling rate and points and whatnot in our data structures, and we're going to apply a noise waveform to it, and we're going to get an error. Okay? So we can see, let's pretend this bottom one is noise. Okay, it's going to be our output. So we're guessing at this wave. So we know what we want it to look like, and in analog, we're guessing at it. Okay? Then we take the difference between those two forms. So we get noise and the desired output. We get the difference, and it gives us this error line. And as we continue to do this, our errors will look more and more like the pulse width modulation wave that we want. Okay? So as we take the difference, we will then integrate the difference between this green wave and this blue wave that is being put on top of it, or rather, and this bottom wave, and it will give us this blue wave that's on top of the green wave. Okay? One more time. We're going to take the difference of the green wave and the bottom wave here, and we're going to show that as this error wave, which is this blue wave going up and down on top of the green one on top. Alright? So what that actually means is now that we're taking the difference, we're subtracting what we want from what we have, and we're integrating that difference. Then we're able to take the integration, and wherever it is over a limit, a specific value, we can turn the pulse width modulation on, and now that we have a guess, right, so we guessed originally, we took noise, and we introduced it into the system, we'll get out a better approximation. Remember, we're doing this at, let's say, 40 times the speed that we need to output the wave. So we can run this a ton of times. So now that we've got the integration and we can guess a new waveform from the integration by turning on the bit here. So you can see the red. The red symbolizes when we are turning on the bit for pulse width modulation. And if I zoom in here really far, you'll be able to see that it's actually just like the sampling rate for this wave, the oversampling rate, which is our very fast rate. We're actually able to look at where this is every fraction of our sampling rate, very small pieces. And we're able to turn on this pulse width modulation wave wherever it is over some value with the integral. I realize this is pretty tough, but basically once we do that, we get a better waveform that we can then use again as a better guess. And then we can continue to do this until the waveform is nearly exactly the wave that we originally wanted. So after doing this a ton of times, we get a pulse width modulation wave that exactly represents the green wave up top. Okay? Please ask questions. You're giving me faces like, Jim, I don't know what you just said. So I need you to kind of articulate it.
How do you know when to stop?
You know when to stop when it's time to deliver the new sampling, the next wave to the output. So we're doing this math digitally, but the noise is generated in analog, okay? And the output is generated in analog, okay? And I realize there's a step missing so far, but I want to make sure that you understand how to get this pulse width modulation from the desired output. So the desired output we know in digital world, in our data structures, and we generate these analog ones and measure them back in, and then we guess, again, over and over, using this integral technique, this integration of our guess, subtracted with the one we want, we get these errors. The errors then, we take the integral goes into this new form, and we keep going through the cycle, where we take the difference, errors, integral, and then have another output. We keep going. We know when to stop, when either we've deemed the wave to be accurate enough. Usually this is a set amount of times, and it's usually calibrated such that it will be exactly when it needs to be delivered, it will finish, and then it will deliver that, just before. You know what I mean? So is this making a little bit of sense?
How's the limit determined?
The limit that we want to switch this bit on and off.
Yeah.
It is some sort of a constant. I don't know.
Okay, so it is set beforehand.
Yes. Yep. Absolutely. It's set beforehand. I believe it has to do with like the zero of the wave. So like I guess in this case it would be like here. Is going to be, does the wave need to be on or off? And it has to do with, it uses the integral and compounds it to that value and then turns this.
Yeah. And then so how do you average them?
So now that you have the pulse width,
Yeah.
how do you create the analog form? Is that what you're saying?
Well, like you said you were doing this like 40 times, right?
Oh, so at the end, you get this output at the bottom.
Yeah.
You understand that?
Yeah.
After every cycle,
Yeah.
that output goes back in as our next guess. So we started with noise, right? And then we do this we do this one cycle. Let's go slower. We do this one cycle, and then we get an output that looks probably not as good as the bottom does, but it looks like something, okay? And it's an approximation. Then we take that output and we put it over our desired wave, and we take the difference, and we'll get errors that look like this red and blue at the top.
Okay.
So the output wave is used in the next cycle as the next guess.
Oh.
Okay?
Yeah, this would have been really helpful to have an animation.
Yeah, I know, I'm sorry. I couldn't find anything on this. This is really hard to dig up. Because everyone's like, it works. Of course it works. You take the integral. There's like lots of math, but I didn't find any animated things. It took me like 2 separate weeks. I had to take multiple hour sessions to try to learn this. And I hope I'm articulating it in a way that you guys can actually understand. Does it make sense? Give me a positive or a negative here. I hate neutral. Thumbs up, thumbs down. Good? Okay. Hopefully online is the same. So this is, in the end, we're going to get this pulse width modulated wave in an analog form, meaning that we have it on a wire somewhere. It's in a trace, it's a real wave generated as output, okay? Then, all we have to do is take a simple filter, a low-pass filter, and run the wave through that, and it generates the sine wave from the pulse width modulation like magic. Because we've done all this work to set it up, and then it just sine wave. We don't have to do anything else. So once you get this approximation just right, you output it, it goes through a very simple filter, which we'll actually look at, because it's so simple, I just threw it in. And we'll see that it generates the sine wave exactly like we want it to. It just does what you would expect it to. It just takes it and it just... But all with some magic electronics capacitor stuff. But yeah, you have to do all this work to be able to get this wave at the bottom. Okay. Whew. That was the hardest part of the presentation. Now everything is going to make sense. Alright? So now we're going to look at one more thing we need to know, and that's called a harmonic. I didn't even know this. I heard the word before, but I didn't actually know what it was until I needed to do this presentation. And it's really simple. So at the top we have a vibrating string. Picture it as like the neck of a guitar. Okay? And at the second one down, the one with 1/2 hovering here, that is the harmonic of the first one because it is a multiple in its wavelength. It is exactly one fraction of the wavelength of the top one. We can also see 1/3 and 2/3 because it's an exact fraction of the top one. It's also going to be a harmonic. You'll also see that 1/4 and 1/8, if it was here, as well as 1/6, are also going to match up. So 1/2, 1/3, 1/6 all match up. 1/4, 1/2, 1/8 all match up. They're all multiples of each other, right? They're like nice perfect fractions. And you'll notice that they'll match up, because if you take 1/3 and you follow this line downwards, what do you get when you get to 1/6, right? It matches that same exact node. Okay? So what a harmonic is it's literally just a wave of a multiple of frequency. So if this top one is 100, this is 50. And it's in a wavelength, whatever unit we're using, doesn't really matter. Adam is literally, I want everybody online to know this, Adam is literally taking a string and watching it vibrate.
No, it's sort of similar to the harmonics. You go like this, and then like, if you do it like really fast, you get 2 harmonics. You get
Right.
a third harmonic. Just like-
Right, you get the wavelength is 1/3 of this total string. So, this is super simple, and it's gonna apply into distortion that we're gonna see introduced from MOSFETs and other types of electronics that are going to process our signal. And it's important that you know this part so that you can kind of understand what the distortion looks like. There's also going to be a video later to show how it actually affects the sound. That's an animation that looks really great. Alright, so now we're going to talk about what a MOSFET is. Can I get a show of hands in here to know, for people who know what this is and how it works? 2, 3, 2.5. Okay, good, I guess. I'm guessing online is just about the same. So this is very simple. It is something super cool that I never knew how it worked until earlier today when I watched the video, and I was like, oh my god, everything makes sense. Everything in the world, I get how the world works now. So this allows us to actually amplify our signal, and we are going to do this. There's a nice video and article here for those of us who have the slides on the computer and want to look into this more. But basically, our source and our drain are, think of that as our wire that we'd like the output signal to go to. We'd like the output signal to go in this direction here. Okay? We'd like it to go out the drain. We have our source is applying a fixed current, a fixed amount of electricity to this piece over here, this N+. It's also important to note that this MOSFET is made of 2 separate things that are important. The other stuff isn't that important. The P-type and the N+ type substrates. N+ has more free electrons than P-type. We're getting down to an atomic level here. So there are free electrons in both the P-type and the